science and natural history related questions all the way from the UK. Dr. Chris Smith, I hope you're well, sir.
I'm doing very well myself. How about you?
I'm okay. It's a lovely foggy day here in Cape Town, not in London town.
Well, we always traditionally begin this programme talking about the weather. We are enjoying a nice autumn, but you can tell autumn's coming. And you get up in the morning and there is the mist there. But the wonderful thing about this time of year, because we are going into winter, you start to get these extraordinary sunrises and sunsets because of the attitude of the sun on the horizon. So we get these amazing, glorious, beautiful colours. But I was also watching the moon rise last night, and because we're at the end of the harvest season, there's still quite a lot of dust in the air. We've also had a long dry spell, and dust in the atmosphere scatters more light. So you also get very yellow moons. So we were watching a very orange moon come up yesterday, exaggerated by that dust in the atmosphere. So there is some payback for the fact that we are going to have a long, gloomy grey spell.
Now let's talk about Jen in Komiki. I see you, but let me just use this introduction of the weather, and let's get the pleasantries out of the way. Firstly, the difference between mist and fog, and how could it be so? What is it, misty or foggy today? If yesterday was quite a balmy, warm day in Cape Town, I think the temperature was around about 25, 26. Breathless day in Cape Town, no wind at all. How could today be so misty / and or foggy? What's the difference?
I think really it's the scale. Fog is really dense, mist is more wishy-washy. You can still see through mist, but it's there. Whereas fog is pretty dense and can have the potential to mean you lose your way trying to find your way around. But they are effectively the same phenomenon, which is it's a cloud at ground level. It's particles of water. How does that happen? Well, in the atmosphere, there is water vapour, because when the sun illuminates the ground or the ocean or a lake or a river, it gives energy to the water, and some of the water molecules have enough energy to break the bonds that hold them as a liquid, and they go off into the atmosphere as water molecules, individual water molecules spread out in space. The temperature holds them apart because they're whizzing around so quickly they don't get close to each other for a very long time to enable them to stick together very well. But as the temperature falls, then it's much easier for those water molecules to stick together. Cold air can't hold as much moisture as warm air. So what you need is a nice warm day to drive the water off of a surface, the land, the lake, the sea and so on, and put the moisture into the atmosphere. But then you need a cold night, which cools down the ground, which in turn cools down the air close to the ground, which in turn means that the molecules of water which are in the air can get close together, join up and form droplets like they do in the clouds, and that gives you small moisture droplets which are small enough to remain suspended close to the ground surface, not too heavy to fall, but small enough but present enough to scatter the light that's coming through. And the reason you can see the stuff is because as light goes through the air, it keeps hitting these tiny droplets of moisture, which has the effect of bending and warping the path of the light, scattering it all over the place. And because that applies equally to all the different wavelengths or colours of light, you see all the colours of light coming to you, and all the colours of light, when added together, look white, which is why fog looks white. It's effectively snow hovering in the air.
Love it. It's so moody and evocative. I love a good foggy day. But Jen in Komiki, thanks so much for holding on. Good morning. What's your question?
Hi, everybody. Good morning, Dr. Chris. My question is, I've just been away. Please excuse me if there's noise. I'm at the auto electric shop. They're fixing things. My question is, I've been away this week, and somebody said to me that if the Earth was 1 kilometer further away from the sun, we'd be frozen and not alive. The planet would be frozen. And if it was 1 kilometer closer to the sun, we'd all be dead from heat. Is this correct?
Hello, Jen. What are you buying in the electric shop?
I'm having my brake pad sorted. I can't
okay.
go anywhere. My brake
Not you personally, your car, I hope. Right. Yeah. The answer to this question is that they're sort of right, but on a bit of a wrong scale. The Earth is 6,000 kilometres between the centre of the Earth and the surface of the Earth on average, about 6,000 kilometres is the radius of the Earth. And if you think about the height of Mount Everest, which is, 29, 30,000 feet, hugely high. Once you work that out, a kilometre's neither here nor there. So they're right in the sense that the Earth is in just the right position in space on planetary scales to be in what we call the Goldilocks zone. Remember Goldilocks and the three bears, the porridge she liked, the chair she liked, the bed she liked was the one that was just right. The Earth is in just the right position relative to the Sun, so that the amount of energy flowing to us from the Sun doesn't cook us out of existence, nor does it plunge us into the deep freeze. It's just right to maintain a steady state where we have liquid water, and that is one of the essential ingredients for life and the stability and balance of life on our planet. If we were much further away from the Sun or much closer to the Sun, this would not be the case, and you just have to look at Mercury cooking away close to the Sun, Venus, runaway greenhouse effect, temperature hot enough to melt lead on the surface of the planet, raining sulfuric acid, not a nice place to live. The Earth, on the other hand, the next nearest planet, perfect for life, of all persuasions to exist. So they are right, but a kilometre, definitely not the case. We wander around on our orbit, and mountains are far more than that. So no, it's not a kilometre, but certainly if we were to have a star that shrank and the Sun cooled down, or the Sun puffed up a bit, which will happen in the future, and made us hotter, we will be in the wrong place. So yes, the Earth is in the right place, but the scale is slightly out. It's not a kilometre, it's much more than that.
So people then ask, then how is it that in the infinity of our universe, how is it that, to borrow from Carl Sagan, that this one singular pale blue dot is the only planet that can sustain the forms of life that we know it in the infiniteness of our galaxy, of our universe? Chris?
Well, it almost certainly isn't, because statistically that doesn't make sense, because we know that the Milky Way, our galaxy alone, which is 100,000 light years across, has got a couple of 100 billion stars in it. And there are probably a couple of 100 billion galaxies like the Milky Way. Therefore, there are about 1 followed by 22 zeros worth of stars out there in the universe. And if each one's got, let's for the sake of easy math, say 10 planets, then you've got 1 out of 10 to the 23 possibilities to find an Earth-like planet. So we think this one is special because we live here, and it's the only one we know of in our cosmic neighbourhood. But when you have something as vast as the universe, on the scale of the universe, the chances of there being another configuration where the star is the right temperature, the planet's the right distance from that star to have liquid water, that's going to exist somewhere else. We just haven't found it yet.
Chris, what makes Jik clean stains and makes clothes white? Jik is what we, as a brand name for bleach here in South Africa. I don't know if you have a similar brand in the UK, but essentially asking what makes bleach clean stains and makes clothes white? A very domestic question, but domesticity is also science, of course.
Right, well, let's not talk about one specific brand name. Let's consider cleaning in general, because there's lots to talk about there. When we wash clothes get dirty because they pick up muck from the environment, and that muck can include mud, it can include grease and oils off of us and the environment, and then things that stick to it, and then of course foodstuffs, which are proteins like tomato sauce. And there is a well-known strong force in nature. There's magnetic force, electrical force. There's also the attraction between a white shirt and tomato sauce. That's a very powerful force indeed. And when the two get together, there's a catastrophe. It's like matter and antimatter, isn't it, when the two meet? But when we wash clothes in that way, washing powders do several things. If they are biological washing powders, the manufacturers have put into the washing powders chemicals, usually enzymes, which have been carefully selected and chosen to work at higher, but not really high, so you can save energy, temperatures. And they have the role of going on to whatever the contamination is on the clothes and using the power of chemistry to dismantle the material that is making the stain and the dirt and dislodge it from the clothing. There are also chemicals in these washing powders called optical brighteners, and what they do is add to the washing powder substances which, after you wash the clothes, are left behind in the clothes, and they have the effect of reflecting more colours of light and also converting some invisible colours of light, like very deep purples and ultraviolet, into colours that we can see so that the clothes give out more light than visibly hits them, making them look brighter and more eye-catching. So that's how general washing powders work: dislodge dirt, dissolve dirt, eat away at dirt, and also make your clothes look clean and bright. But there are other ways to clean things with bleaches, and bleaches are chemicals which include chlorine-containing chemicals which have the ability to do oxidation. When we have a bleach, you can have peroxide, works as a bleach, the stuff you put on your contact lenses or on your teeth and dentures and so on. You can also use bleach hypochlorite containing chemicals. Although the source of the oxidizing is different, the outcome is the same, which is you're producing a highly reactive chemical species which has the ability to rip electrons off of things because it's hungry for electrons, and as it does so, it causes the thing to fall apart. And in fact, yesterday I was having a very interesting conversation with a chap in Queen's University Belfast in Northern Ireland, and he has invented a way to make plastic that self-sterilises. So we could make aprons and gloves for hospital use, for example, so if any viruses or bacteria fall on there, it kills it. How does it do it? Because it's got chemistry, it's got titanium dioxide, the same stuff you put in white paint actually, in the surface. Light hits it and it then turns oxygen in the nearby air into reactive oxygen species, effectively bleach, and that then attacks viruses and it attacks bacteria, pulls them to pieces, ripping electrons off their surfaces and makes them break, and as a result they can no longer infect anybody. And that's basically what we do when we swab a surface down with bleach to clean it.
We spoke about hair bleaching before, people who spend a lot of time in the sun. Would this be, particularly if you spend a lot of time in seawater and spend a lot of time on the beach? Definitely sometimes when I have spent my summers as a beach baby, even my hair bleaches a little bit in terms of the sunlight. Is there a similar phenomenon that happens when we're talking about, store-bought domestic detergent, bleach, and what happens in the bleaching of our clothes and even our hair?
You lay on the beach and sunlight produces or results in reactions with the surface of your hair which produce these charged or reactive species like this person Andrew Mills plastic. It will produce reactive molecules that will then leap onto the melanin that makes our hair a dark colour and attack it, break it down, and if you break down the melanin, it stops being black or brown or a golden colour and becomes more white, so your hair does look lighter if you get a lot of sunlight on it. Go to the swimming pool, spend a lot of time in the swimming pool, you're going to see the same thing happen because the chlorine, which is it's actually hypochlorite in the swimming pool, will also do the same thing. The chlorine molecules will attack the colour molecules in your hair, making them look lighter, and peroxide, hydrogen peroxide, does the same thing. It doesn't produce chlorine, it produces peroxide, but at the same time this is also oxidizing and will attack the colour molecules in your hair, the melanins, and make them look whiter so your hair looks lighter.
Chris, just how deafening was the Big Bang? And what was the first ever sound heard on Earth, do you think? Would the Big Bang have heard in the vacuum of space? Sound needs air, or at least not a substance, but something to help it travel. Was there even a sound with a Big Bang in the vacuum of space?
No, we wouldn't have heard the Big Bang because, as you correctly say, that sound requires a medium to travel through. And in the vacuum of space, as the Big Bang had happened, which happened in a fraction of a second, then it would have been a big outpouring of energy producing initially heat, but then subsequently material and matter. There wouldn't have been anyone there to hear it for a start. So is the sound there if there's no one to hear it? That's a philosophical argument, isn't it? But if you've got the void of space and you've then got this energy rippling out through space, if there is nothing for it to convey through or make vibrate, then that is not a sound. And we actually did the experiment to show this a few years ago. We sent a balloon to the edge of space and we included with it a computer which was playing screams sent in by people all around the world, including some people from South Africa who sent in some screams for us to play. And we made recordings of those screams at different altitudes. And when we got to the edge of space at about 33 kilometers up, you could no longer hear the screams being played by the computer into a microphone because there was no atmosphere. The atmosphere was so thin by 33 kilometers up that you couldn't hear anything anymore. So the Big Bang would have been a release of a huge amount of energy, but we wouldn't have been able to hear it if you were standing at a distance as it went past, because there would be nothing to convey the energy to you. So you do need a medium for sound to travel through, whether that's a gas or it's a metal or even a liquid. Sound travels very well in all of those things because it is a compression wave. It is atoms and molecules bashing into each other and conveying a force through the material until it gets to your ear, where the air in your ear canal then bashes into your eardrum and makes it vibrate in the same way, and that is then conveyed across 3 tiny bones into your inner ear, which then converts those sound waves into brain waves.
What was the tagline for the movie Alien? In space, no one can hear you scream.
Yeah, and that's why we tested in space, can anyone hear you scream? And the answer is no, they absolutely couldn't. We couldn't hear a thing.
Quick voice note, you can still get your questions coming in on 0214460567 to Dr. Chris Smith, the Naked Scientist. But let's hear some of our voice notes.
Dr. Chris. My partner's name is Chris, so he always listens with interest. Can you please explain about rainwater and how it manages to get the stains out of things? Because I'm finding it works, and I believe it's because there's hydrochloric acid in rainwater. Lots of love from Karen and Glencairn.
Chris?
Well, from one Chris to another Chris and family, the answer is that rainwater is just fresh water, and there will be some stuff from the atmosphere dissolved in it. There may be some carbonic acid there because there's carbon dioxide in the atmosphere. There's a bit of sulfur dioxide, especially over more industrialized places, and that makes sulfuric and sulfurous acid. There might be a tiny bit of hydrochloric acid. I find that very unlikely because we are quite sensitive to the smell of that, and I think if we were picking that up in the atmosphere, we would probably notice. I would say it's more likely that it's fresh water, it's not hard water. If you use rainwater because it hasn't got things like calcium salts dissolved in it, especially if you live around some parts of the world, especially around Joburg, for example, people are always replacing their water heaters, for example. Loads of dolomitic limestone there, which dissolves and makes the water very hard. Other bits of South Africa the same. So if you've got hardness in the water, it makes your detergent work much less well because the soap and the detergent gets bound up with the calcium, which is dissolved in the water as temporary hardness, and so you have to add tons more soap to get the same effect. Rainwater doesn't have those dissolved calcium salts in it, so your detergent is going to go further. So I think one explanation for this question is that the rainwater is softer water, doesn't have the temporary and permanent hardness in it, therefore the soap you're adding is going to go further and probably therefore work better.
Lauren in Milnerton, good morning, how are you? It's a very hydro-focused Naked Scientist this morning. You're also wanting to answer a question about water.
Yes, please. I'd like to know how come when you switch on the hot water tap, often the water is white for a few seconds and then it goes clear again.
Good question.
I'd need to have a look at what you mean, but I think what you're referring to, if I've seen the same phenomenon, it's tiny bubbles in the water. And what could be happening here is that when the water is in the pipe, it's under pressure. As you let the water out of the pipe and it flows into the glass or the tank or whatever, it's obviously degassing. The pressure has come off because it's coming from high pressure into the room, which is at low pressure. And if you take the pressure off of a liquid, then anything dissolved in the liquid will come out of solution, and there will be traces of gas dissolved in the water. So it may be that gas then comes out and makes that fine array of bubbles because of the pressure. That would be my speculation. But if anyone knows better, any plumbers listening, please do let us know.
Do you have a fairly old or new geyser, Lauren?
Well, it often happens when you replace a geyser and then it goes away. In this instance, it's not going away, so we're thinking it's a potential problem with pipe sizing increasing in pressure, as the Naked Scientist said, causing the white bubbles.
Thanks so much. What about calcification around the element of a kettle or of a big kettle, a geyser, particularly in municipal tap water, or maybe still has lots of minerals in? Could the calcification of a heating element also have something to do with a cloudiness of water, Chris?
You would have thought it would be permanent. If it were adding stuff to the water, bits of calcium, flakes of scale, it would A, sink, and B, it would be there permanently. What is being referred to here, I've seen this, is that when you first fill a glass, there are white bubbles in it which slowly clear, often from the bottom going up to the top, and it clears away. They're white because if you've got millions of tiny bubbles in the water, when light goes into the glass, it sees these bubbles, which are a different medium than the water, and so the light changes speed between the water and the bubble, and this has the effect of bending the light, and so you reflect a lot of light back out of the glass at you, and because this affects all the different colours of light equally, you mix all the different colours together, you see white, which is why this looks like a white layer, and then as the bubbles dissipate and dissolve or escape out the surface of the glass, you then get the clarification. It goes completely clear again because that effect goes away. Now that wouldn't happen if it was some kind of solids or something dissolved in there like flakes of calcium. So I think this is a gas phenomenon. I think it's degassing because you've taken the pressure off of the glass of the water as it comes out the pipe.
Keith asked, why doesn't super glue get hard in the container?
Well, super glue is actually a cyanide based material, and it requires a bit of moisture to set. So surfaces need to be rough and porous and have some moisture on them. Super glue does not work at all well. The chemical reaction that sets the glue does not work well if you don't have a bit of moisture. This is why it's so good at gluing fingers and other things that you don't want to stick together. And if you try it on metal surfaces, it's much less good because they're not naturally porous or wet, so they won't glue terribly well together with super glue. And the inside of the tube they're usually an aluminized tube, and so as a result of that, it's dry, it's metal, and it won't go off.
I think Rick will be our last question this morning. And Rick asks, if we could hear very low sound frequencies, could we hear gravitational waves? I'll add a little addition to that. Is that why we have reports that animals are largely good predictors of whether there's any seismic activity, because they're able to hear lower frequencies of sound, and they could hear essentially an earthquake before it happens, Chris?
Gravitational waves are very, very difficult to detect, which is why when it was eventually proven that they existed and researchers including Kip Thorne in America detected them, they got the Nobel Prize for doing it, because the detectors that detect gravitational waves are exquisitely sensitive, and they are detecting tiny displacements of enormous objects which are mirrors over reflecting light over really long distances, and they're moving by fractions of the size of an atom, and that's actually how they're able to detect the gravitational waves. Your ears cannot do that, so you wouldn't be able to hear them, but you can certainly think of the phenomenon used to detect them as a bit similar to how your ears actually work by making things displace when sound waves vibrate them, and that is sort of similar to what the scientists did to find gravitational waves, but the resolution would have to be very, very good. You'd have to have enormous ears that were extremely good in order to hear them.
And that's it for this week. Dr. Chris Smith, I hope you enjoy your weekend. Looking forward to chatting to you next week. Stay well, good sir. Enjoy whatever warmer weather you still have.
I will do my best. Go well, Leicester.